Welcome. This is a documentary lecture on the Brownian heat engine, presented by Dr. Mesfin Asfaw of West Los Angeles College. A Brownian heat engine is a tiny engine, powered not by pistons or gasoline, but by random thermal motion. In this lecture, we will show how chaos at the smallest scales can be organized into useful work, and we will see new results, from my own published research in Physical Review on how smooth temperature profiles outperform the conventional two-bath model. Suspend a small particle in water and watch it under a microscope. It refuses to be still. It jitters, drifts, and reverses, tracing an erratic path with no apparent direction. This is Brownian motion, first observed by the botanist Robert Brown in 1827, and explained by Einstein nearly 80 years later. The water around the particle looks calm. But beneath that surface, billions of molecules collide with it every microsecond, far too small and too fast for the eye to resolve. At every instant, more impacts arrive from one side than the other. The particle is pushed. A moment later, the imbalance reverses. On average, a Brownian particle does not drift. Its mean displacement is zero. But its mean squared displacement grows steadily in time. The particle remembers nothing. Each step is independent of the last. The cloud of possible positions widens with the square root of time. Zoom out. A drop of ink in still water. The microscopic randomness of each molecule, summed over astronomical numbers, becomes something visible, a smooth, predictable spreading we call diffusion. Random microscopic motion creates regular macroscopic spreading. Heat is not an abstract quantity. It is the kinetic energy of molecular motion. Raise the temperature, and molecules move faster, deliver harder kicks, and Brownian particles jitter more violently. Diffusion grows linearly with temperature, and inversely with friction. Random kicks are not the only force acting on the particle. The fluid also resists motion. The particle is always being pushed, and always being slowed. Random kicks and friction balance one another. This balance is the foundation of equilibrium physics. We can write Newton's law for a Brownian particle, ignoring inertia in the heavily damped regime. Three things determine its motion: friction, the gradient of an energy landscape, and a random thermal force. This is the Langevin equation. Place the particle in a smooth bowl-shaped potential at constant temperature. It explores the bowl. It reaches a stationary distribution. It fluctuates forever, but it never produces work. Random motion alone is not enough to make an engine. In a symmetric environment at thermal equilibrium, leftward and rightward motions cancel statistically. The mean velocity is zero. No bias, no current, no work. To extract anything useful, we must break the symmetry. This is the central question of microscopic engineering. To convert chaos into directed work, three ingredients are required. Fluctuation, a source of random thermal motion. Broken symmetry, an asymmetric structure or environment. And non-equilibrium driving, an energy input from outside. Remove any one of them, and the engine fails. A potential is symmetric if it looks the same forwards and backwards. In such a valley, every leftward path has a mirror image rightward path with identical probability. The particle has no reason to prefer one direction over the other. Now break the symmetry. tilt one wall steeper than the other. The result is a sawtooth, a periodic potential where each tooth has a gentle slope and a sharp cliff. But here is the surprise: at thermal equilibrium, even this asymmetric landscape produces no current. Asymmetry is necessary, but not sufficient. A particle in a periodic asymmetric potential experiences different barrier heights when looking left versus right. Each cell has a steep face and a shallow face. This is the architecture of every Brownian motor, the canvas onto which we will paint our engine. A deep theorem of equilibrium statistical mechanics, called detailed balance, guarantees that the probability current vanishes at thermal equilibrium, even when the potential is asymmetric. A truly autonomous Maxwell's demon is impossible. To make a ratchet work, we must add non-equilibrium driving. There are 5 common ways to push a Brownian system away from thermal equilibrium. A flashing potential, that turns on and off. A rocking force, that tilts the landscape periodically. A temperature gradient, that couples the system to 2 thermal baths. Chemical energy, like the burning of ATP in a molecular motor. Or an external load. Each of these defines a distinct family of Brownian motor. A Brownian motor is a system that rectifies thermal fluctuations into directed motion, using broken symmetry and non-equilibrium driving. It does not amplify noise. It selects from noise. It uses energy not to push the particle, but to repeatedly reset the conditions under which the particle's random walk has a preferred direction. The flashing ratchet is the simplest Brownian motor. When the potential is off, the particle diffuses freely on a flat landscape. When the potential is on, the particle slides into the nearest minimum. Because the potential is asymmetric, the nearest minimum is more often in one direction. Repeated flashing produces net drift, without ever pushing the particle. Watch the simulation. Toggle the potential on and off. During the on phase, particles aggregate at the asymmetric minima. During the off phase, they spread by diffusion. The drift is statistical, not mechanical. There is an optimal flashing frequency. Too fast, and the particle has no time to diffuse. Too slow, and the diffusion symmetrizes around each minimum. The rocking ratchet works differently. We apply a periodic external force that tilts the asymmetric potential first one way, then the other. On average, the applied force is 0. But because the potential is asymmetric, the particle's response to a positive tilt differs from its response to a negative tilt. The result is a net current. Watch the sawtooth tip back and forth. During the favorable half of the cycle, the particle has just enough energy to roll over the gentle slope. During the unfavorable half, the steep wall blocks it. The particle hops 1 tooth per cycle, on average. Random kicks help it climb when it needs to. Now we introduce 2 temperatures. A hot region and a cold region, alternating in space. Here is a remarkable point that is often misunderstood. For the thermal Brownian motor, ratchet asymmetry is not required. Even a perfectly symmetric periodic potential, when coupled to a spatially varying temperature, produces a net current. The temperature profile itself breaks the symmetry. The hot regions inject kinetic energy on one side, the cold regions absorb it on the other, and a directed flow emerges. Asymmetry helps, but it is the temperature gradient that drives the engine. Watch the simulation. Even with a perfectly symmetric cosine potential, the particle drifts when one half period is hot and the other is cold. Toggle between the symmetric and the asymmetric ratchet to see for yourself. The current persists in both. Asymmetry merely amplifies the effect. The temperature gradient is the true engine. Beyond the simple two-bath model, my own work in Physical Review E in 2025 showed that the particular shape of the temperature profile matters enormously. Consider an exponentially decreasing temperature along the reaction coordinate, a configuration that closely mimics laser-induced thermal gradients and thermoplasmonic heating in real experiments. The result is dramatic. The particle velocity becomes significantly larger than in the conventional two-bath, piecewise constant case. Watch the particle drift in this exponential thermal landscape, and compare it to the standard two-bath result. A second smooth profile, also from my work in Physical Review E in 2022, is a linearly decreasing temperature along the reaction coordinate. Here, T of x decreases as a straight line. Like the exponential case, this configuration generates a directed current that exceeds what the two-bath alternation produces. Compare the three side by side: two baths, linear, and exponential. The smoother the temperature profile, the stronger the drift. Now we hang a small weight on the particle. A constant force resists the motor's natural direction. If the motor still moves forward against the load, it does mechanical work on the load. That, in essence, is the definition of an engine. Mechanical work is force multiplied by displacement. Each time the particle climbs one ratchet tooth in the loaded direction, energy is transferred from the thermal bath to the load. The hot reservoir cools by exactly that amount, plus the inevitable losses to dissipation. A classical heat engine, whether Carnot, Stirling, or Otto, requires four ingredients: a hot reservoir, a cold reservoir, a working substance that exchanges heat with both, and a mechanism by which the working substance does work. A Brownian heat engine has all four. The difference is that the working substance is a single particle. Here is our definition. A Brownian heat engine is a microscopic engine in which a Brownian particle, coupled to two thermal reservoirs through an asymmetric potential, converts the temperature difference between the reservoirs into mechanical work against an external load. In a steam engine, gas expands and pushes a piston. In a Brownian engine, the particle fluctuates against an asymmetric landscape and inches a load forward, one thermal kick at a time. The same thermodynamics applies. The same Carnot bound limits efficiency. The mathematics is identical. Only the scale changes. We couple alternating regions of the ratchet to two reservoirs. In the hot region, kicks are violent. The particle has enough energy to climb steep walls. In the cold region, kicks are weak. The particle settles into wells and is trapped by the asymmetry. Heat flows from hot to cold, and along the way, it does work. Now add a load. The effective potential the particle sees is the bare ratchet, plus a linear tilt. The load tilts the energy landscape uphill in the direction of motion. Climbing requires energy. That energy must come from the hot reservoir. With no load, the motor still moves. Drift, caused by the temperature difference and the asymmetric potential, sweeps the particle forward. But it does no useful work. Motion alone is not engine work. An engine must lift something. Now add a small load. The drift slows. But if the temperature difference is large enough, the motor still moves forward, and now it is doing real work. Energy flows from the hot bath into the particle and out to the load. The particle is the converter. The asymmetry is the rectifier. Increase the load. The drift slows further. At a critical value, called the stall force, the motor stops. Beyond the stall force, the motor runs in reverse. The load now drives the particle backward, and the engine becomes a refrigerator. The motor moves forward when the driving, that is, the temperature difference plus the asymmetry, exceeds the resistance, that is, the barriers plus the load. The hot bath supplies the energy to climb. The asymmetry decides which way climbing leads to escape. The cold bath traps the particle into the next minimum. The load opposes everything. Net forward motion appears only when driving wins. The engine fails in 5 distinct ways. When the load exceeds the stall force. When the temperature difference is too small. When the barriers are so high that no fluctuation can cross. When the noise is so weak that crossings are exponentially rare. Or when the flashing or rocking frequency is mistuned. Power is the rate at which the motor does work on the load. At zero load, the motor is fast, but does no work. At the stall load, it does no work because it does not move. Maximum power lies somewhere in between, typically near half the stall force. Efficiency is work output divided by heat input from the hot reservoir. Like every heat engine, the Brownian engine is bounded by Carnot. Efficiency cannot exceed 1 minus the ratio of cold to hot temperatures. Real Brownian engines achieve only a fraction of this bound, because every barrier crossing dissipates heat. The motor does not violate the second law of thermodynamics. It satisfies it. Total entropy production is always non-negative. Useful work is extracted only by paying an entropic cost, heat dumped into the cold bath. The motor is a fluctuation rectifier, not a perpetual motion machine. All the elements come together here. The asymmetric ratchet potential, fixed in place. The hot zones and the cold zones. The Brownian particle, walking from left to right under the combined influence of thermal fluctuations and a rightward drive. Watch it traverse the landscape. Each pass to the right is one cycle of the engine. Adjust the controls and see how temperature, asymmetry, and friction change everything. Let us summarize the lessons of this lecture. Brownian motion is intrinsically random. Random motion is unbiased at thermal equilibrium. Directed motion requires that some symmetry be broken either by an asymmetric potential or, as my own work has shown, by a spatially varying temperature alone. Non-equilibrium driving supplies the energy. A load converts directed motion into useful work. And smooth temperature profiles, exponential or linear, outperform the conventional two-bath model. A Brownian heat engine is what emerges when all of these elements come together. A Brownian heat engine teaches a single, profound lesson. At microscopic scales, noise is not merely disorder. Under the right conditions, broken symmetry, or a temperature gradient, and a flow of energy, random thermal motion can be organized, channeled, and converted into directed work. Randomness, properly harnessed, becomes work. Thank you for watching. This has been a documentary lecture by Dr. Mesfin of West Los Angeles College.